Hello and welcome back to the Wunder Lab. I'm so glad you're here. Tonight, we're going to take a slow, gentle stroll through the curious world of memory and forgetting. The soft unraveling of why some moments vanish while others linger like old perfume on a sweater. This is a video about the beauty and in the grand theater of the universe. There exist objects so extreme, so incomprehensible, that even light, the fastest thing known to physics, cannot escape their grasp. These are black holes. To the human mind, they are symbols of mystery, danger, and paradox. But to physics, they are the ultimate laboratories of reality, where space, time, energy, and information converge into one impossible point. A black hole is not an object in the traditional sense. It is a region of space-time where gravity has become absolute, a place where the known laws of physics collapse into silence. Yet, within this silence lies a profound order. For decades, scientists believed black holes were cosmic destroyers. Today, they are increasingly seen as the universe's ultimate data processors, capable of storing, transforming, and perhaps even transmitting the fundamental information that defines existence itself. But to understand why, we must first trace their origin. Every black hole begins as a star, a sphere of nuclear fire balanced precariously between gravity and radiation. Inside its core, hydrogen atoms fuse into helium, releasing colossal amounts of energy. This radiation pushes outward, countering the inward pull of gravity. For millions, sometimes billions of years, this balance sustains a star's life. Yet every star has a limit. When its fuel is exhausted, gravity begins to win. The outward pressure fades and the star collapses inward. For small stars, this collapse ends gently. They cool into white dwarfs or fade as neutron stars. But for the most massive stars, the collapse becomes unstoppable. Gravity crushes matter beyond recognition, shrinking the dying star into a singularity, a point of infinite density and zero volume. Surrounding this point is the event horizon, the boundary beyond which escape is impossible. The moment something crosses it, even light, it is lost to the external universe forever. At least that's what we once thought. To an outside observer, the event horizon marks the end of knowledge, but to the laws of physics, it marks the beginning of the deepest questions ever asked. What happens to information inside a black hole? And if information truly disappears, does that mean the universe itself can lose knowledge of its own past? The nature of space and time. Albert Einstein's theory of general relativity tells us that gravity is not a force, but the curvature of space-time itself. Matter tells space how to curve, and space tells matter how to move. In this elegant geometry, a black hole is simply a region where curvature becomes extreme, where space-time folds in on itself so deeply that all paths lead inward. From the outside, time near a black hole slows dramatically. To a distant observer, an object falling toward the event horizon appears to slow, redshift, and freeze in time. To the object itself, however, time continues normally as it plunges inward. This duality, of time halting for one observer while continuing for another, is one of the most mind-bending features of relativity, and it gets stranger still. At the singularity, the known equations of physics fail completely. Space and time lose meaning. The universe as we define it stops making sense. What lies beyond that veil remains one of the greatest mysteries in science. In the 1970s, Stephen Hawking proposed something revolutionary. Using quantum mechanics, he showed that black holes are not entirely black. Instead, they emit faint radiation, now known as Hawking radiation, caused by quantum fluctuations near the event horizon. This radiation slowly drains a black hole's mass, meaning black holes can evaporate over time. But Hawking's discovery created a paradox, perhaps the most profound in all of physics. If black holes evaporate and everything that falls into them disappears, then information is destroyed. Yet quantum mechanics insists that information can never be lost, that every particle, every quantum state, must in principle be recoverable. This clash between relativity and quantum theory, between gravity and information, defines modern physics. It is a conflict not just of equations but of ideas about reality itself. Is the universe a perfect record keeper? Or does it allow information, the very fabric of existence, to vanish? Recent theories suggest black holes may not destroy information at all. Instead, they may encode it, storing data about everything that falls inside, somehow woven into the surface of the event horizon. This idea is known as the holographic principle, and it changes everything we think we know about space and time. According to this view, the three-dimensional contents of a black hole are projected on its two-dimensional surface, just as a hologram encodes a 3D image on a flat sheet of film. In other words, a black hole might act as a vast cosmic hard drive compressing every atom, photon, and quantum bit of information that enters it onto its surface, never truly losing anything, merely transforming it into another form. If this principle holds true, then the universe itself might be holographic, not made of solid matter, but of information, encoded across cosmic boundaries. Black holes are the most efficient information storage devices in nature. Their entropy, a measure of how much information they can contain, is proportional not to their volume, but to their surface area. This strange property, discovered by Jacob Bekenstein, suggests a deep link between gravity, thermodynamics, and information theory. Every black hole radiates energy like a perfect black body following precise thermodynamic laws. In fact, the 4 laws of black hole mechanics mirror the 4 laws of thermodynamics, a symmetry that hints that the physics of space and the physics of heat are connected at the most fundamental level. It is as if the universe is whispering, information is never lost. It only changes form, yet we are far from understanding how this transformation works. When quantum physics and general relativity meet inside a black hole, both cease to function properly. To decode what happens there, we may need a theory of quantum gravity, a framework that unites the very large and the very small. Some researchers believe this theory may arise from string theory, where every particle is a vibration of a tiny, one-dimensional string. Others explore loop quantum gravity, imagining space-time as a fabric woven from discrete loops of quantum information. Whatever the final theory may be, one thing is certain: black holes will be the proving ground. They are nature's ultimate stress test for every physical law we have ever written. To grasp the true power of black holes, we must first realize how they reshape the very geometry of the universe. Imagine a fabric stretched taut. This is space-time. Now, picture placing a massive object on that fabric. It bends, distorts, and pulls everything around it inward. A black hole is not just a dent in this cosmic fabric. It is a bottomless well, a place where the fabric itself folds inward so steeply that every path, every direction leads down. For light, which normally travels in straight lines, this distortion becomes a trap. Photons circle endlessly near the edge of the event horizon in a region known as the photon sphere. If they venture slightly too close, they fall inward forever. Slightly farther out, they escape, their paths curved and stretched by gravity's relentless pull. This gravitational warping does not only bend light, it warps time. For an observer near the event horizon, seconds tick slower than those far away. In a sense, a black hole is not just a place where light ends. It is a place where time itself ends. When astronomers first confirmed the existence of black holes, they expected emptiness, dark spheres devouring anything nearby. Instead, they found brilliance. The regions surrounding black holes glow brighter than any known object in the cosmos. As matter spirals inward, it forms an accretion disk, a swirling whirlpool of gas and dust, heated to millions of degrees by friction and magnetic turbulence. In its final moments before crossing the event horizon, this matter releases tremendous energy, producing powerful X-rays, gamma rays, and jets of plasma that can extend for thousands of light years. These relativistic jets are among the most spectacular sights in astronomy. They shoot out from the poles of rotating black holes at nearly the speed of light, carrying enormous energy into surrounding galaxies. How these jets form remains one of modern astrophysics' great puzzles. Some theories suggest they result from magnetic fields twisted by the black hole's spin, an immense cosmic dynamo channeling energy from rotation into space. In this sense, black holes are not just destroyers. They are creators, shaping galaxies and regulating star formation through their immense feedback power. The centers of most galaxies, including our own Milky Way, host supermassive black holes millions or even billions of times more massive than our Sun. At the center of our galaxy lies Sagittarius A, a supermassive black hole about 4 million solar masses. For decades it hid behind clouds of dust and gas. But by tracking the orbits of nearby stars, astronomers revealed the invisible giant's presence. These stars whip around the galactic center at astonishing speeds, completing orbits in just a few years, proof of a mass so concentrated that only a black hole could explain it. In 2019, the Event Horizon Telescope, a global network of radio observatories acting as one Earth-sized lens, achieved the impossible, the first image of a black hole's shadow. The faint ring of light surrounding darkness became an icon of human curiosity, a triumph of physics and perseverance. That image wasn't just a photograph. It was a measurement of gravity itself, a direct observation of Einstein's predictions in action. For the first time, we could see the boundary between visibility and oblivion, the edge of forever. Black holes are not merely residents of galaxies. They are their architects. Evidence shows that the mass of a galaxy's central black hole is linked to the total mass of the galaxy's stars, a relationship known as the M-sigma relation. This connection suggests that as black holes grow by consuming matter, they also influence the evolution of their host galaxies. Through their jets and radiation, black holes can heat surrounding gas, preventing it from cooling and forming new stars. In this way, they regulate cosmic growth, acting as thermostats for entire galaxies. Without them, the universe might look very different, perhaps overrun with chaotic starbursts and unstable structures. Paradoxically, the most destructive forces in nature also bring order. From chaos, structure emerges. For all their vastness, black holes are defined by a surface that has no substance, the event horizon. It is not a wall or barrier. It is a point of no return. But on the quantum scale, it might hold the key to unifying the deepest laws of physics. Some scientists imagine the horizon as a quantum membrane, vibrating with information. Each bit on this surface encodes the data of everything that has ever crossed it. This concept transforms the event horizon from a region of mystery into a cosmic information processor, a dynamic interface between what we can know and what lies beyond knowing. If true, this means black holes act like computers, operating on the most fundamental data of the universe. When matter and energy fall in, the horizon rearranges its quantum bits, storing the record of that transformation. What emerges, perhaps as Hawking radiation or gravitational waves, may carry traces of the original information, scrambled but preserved. This vision places black holes at the crossroads of physics and computation, suggesting that the universe itself may behave like a vast quantum computer, continuously processing and preserving information through every star, particle, and black hole. When two black holes merge, they create ripples in space-time, gravitational waves that travel across the cosmos, stretching and compressing reality itself. These waves were first predicted by Einstein in 1916 and finally detected a century later. In 2015, by the LIGO Observatory, each gravitational wave carries a signature, a unique pattern that encodes the story of the collision, the masses, spins, and orbits of the black holes that created it. In effect, the universe broadcasts its own history through space-time vibrations. By studying these waves, scientists can peer into regions otherwise hidden by darkness. Black hole mergers not only reveal how these cosmic giants form and grow, but also offer new ways to test fundamental physics under conditions impossible to reproduce on Earth. In a profound sense, every ripple is a message from the edge of time, carrying the imprint of cosmic events billions of years old, pure information written in gravity's own language. And yet, the deeper we peer into the nature of black holes, the more elusive truth becomes. Each discovery opens another question: what lies beyond the singularity? Can information ever truly be recovered? Is a black hole the end of a story or the beginning of another? Some physicists suggest that a black hole's interior could be a gateway, not to another universe in the science fiction sense, but to a quantum bridge, a region where space-time reconnects in unexpected ways. These theoretical constructs, called Einstein-Rosen bridges or wormholes, might link distant regions of the cosmos or even different timelines of the same universe. Whether such bridges exist remains speculative, but the mathematics behind them continues to inspire new generations of scientists seeking a unified picture of reality. To understand what happens deep inside a black hole, we must venture beyond the limits of our imagination into a region where the concepts of space and time lose all familiar meaning. The singularity at the heart of a black hole is not merely a point, it is a boundary in mathematics where equations yield infinity, and the physical world seems to dissolve into abstraction. But perhaps the singularity is not the true end. It may instead signal the need for a new language of physics, one that replaces infinities with structure, a quantum geometry that underlies the universe's fabric. The search for quantum gravity physicists have long sought to merge Einstein's general relativity with quantum mechanics into a single theory of quantum gravity. In this search, black holes serve as the ultimate testing ground. In string theory, matter and energy are composed of tiny vibrating strings whose oscillations create the particles we observe. Under certain conditions, these strings predict that the information content of a black hole, its entropy, can indeed be represented by quantum states on its surface, confirming the Bekenstein-Hawking formula. This discovery gave theoretical support to the holographic principle and suggested that spacetime itself may emerge from networks of entangled information. Other approaches, like loop quantum gravity, imagine space-time as a discrete lattice, woven from loops of energy, each loop carrying a quantum of area or volume. In such models, the singularity never forms. Instead, the collapsing matter rebounds in a quantum bounce, possibly giving birth to a new region of space-time, perhaps even another universe. While we cannot yet verify these theories experimentally, they offer a profound vision, black holes as portals of transformation, where old space dies and new space is born. Black holes, and the arrow of time. Every physical process in the universe obeys one fundamental rule, the second law of thermodynamics, which states that entropy, or disorder, must always increase. In simple terms, time flows in one direction because the universe tends toward greater complexity. Black holes embody this principle on the grandest scale. Their entropy, proportional to their surface area, represents the maximum amount of information that can be stored within a given region of space. As they consume matter and radiation, they drive the universe toward higher entropy, helping define the arrow of time itself. And yet, the eventual evaporation of black holes through Hawking radiation hints at a cosmic cycle: creation, transformation, and dissolution, where even the most permanent objects fade away, returning their energy and perhaps their encoded information to the universe. In this way, black holes may act as timekeepers of entropy, regulating the balance between order and chaos across cosmic history. Although black holes seem eternal, they are not. Hawking radiation slowly robs them of mass, photon by photon, over incomprehensible spans of time. A stellar mass black hole might take 10 to 67 years to evaporate. A supermassive one, perhaps 200 years or more. As they shrink, they grow hotter, their radiation intensifying until, in their final moments, they release an immense burst of energy, a brief flash marking the end of an object that once ruled entire galaxies. What remains after this final evaporation? Some theories predict a faint cloud of high-energy particles. Others propose a Planck-scale remnant, a stable nugget of pure quantum gravity preserving the last trace of information. If the universe endures long enough, these fading black holes may represent its final light, the last whispers of structure before cosmic darkness returns. Stephen Hawking once believed that information was truly lost when black holes evaporated. Later, he reconsidered, proposing that subtle quantum correlations in the radiation might encode the information that fell in, though in a highly scrambled form. This debate gave rise to the concept of black hole complementarity, suggesting that information is both reflected at the horizon and passes through it, depending on the observer's frame of reference. To the distant viewer, the data remains encoded on the surface. To the infalling observer, it continues inward unimpeded. No single perspective captures the full truth, but together they maintain the consistency of physics. Recent research, particularly from the study of quantum entanglement and ADS-CFT correspondence, a realization of the holographic principle, strengthens the view that information is preserved. The event horizon behaves like a screen storing quantum data, while the interior of the black hole is a holographic projection of that information. In essence, the laws of physics appear to protect information as sacred. It may change form, but it cannot vanish if information is preserved and black holes process it through quantum interactions at the horizon. Then these objects function like natural computers. Each bit of information corresponds to a quantum of area, a unit smaller than any human technology can conceive. Theoretical calculations suggest that a black hole can perform more computations per second than any artificial machine ever could, processing energy and data at the ultimate limit allowed by physics. In this view, the universe is not only a stage of matter and energy, but an ongoing computation of information, a digital cosmos where black holes act as the processors, stars as power sources, and space-time as memory itself. Every collision, decay, and radiation event is a line of code in the grand algorithm of reality. Through this lens, black holes become less like cosmic tombs and more like cosmic engines, maintaining the conservation and transformation of information across eternity. Why do these distant phenomena captivate us so deeply? Perhaps because black holes reflect something essential about ourselves, the urge to seek, to question, to understand what lies beyond the horizon of knowledge. They remind us that the universe is not simply vast, but structured, governed by rules both mysterious and precise. They show that even the darkest regions are filled with logic, meaning, and potential discovery. Our pursuit of black holes is, in truth, a pursuit of understanding reality itself, of finding where knowledge ends and imagination begins. As we reach the edge of understanding, black holes stand before us like mirrors, reflecting not only the structure of the cosmos, but the limits of human knowledge itself. For centuries, they were the monsters of our imagination, symbols of finality and annihilation. Today, they are gateways to a deeper truth. That information, structure, and even consciousness may be woven into the same fabric that shapes the stars. The story of black holes is not one of destruction, but of preservation. Each atom, each photon, each vibration that falls beyond the event horizon contributes to an ever-growing cosmic record, a ledger of existence written not in ink or light, but in geometry and time. What we once feared as the end of knowledge may, in fact, be its highest expression. Black holes and the fate of the universe. To understand the ultimate destiny of black holes is to glimpse the farthest future of the cosmos. Our universe is expanding, and as it does, galaxies drift apart, stars burn out, and light itself grows dimmer. In the far future, long after the last stars have faded, only black holes will remain. They will dominate the dark era of the universe, quietly consuming stray matter and radiation. For eons beyond measure, they will persist, silent anchors in a sea of emptiness. But even they will not last forever. As Hawking radiation continues its slow, relentless work, black holes will evaporate one by one, until the universe is left cold and empty, a thin mist of low-energy particles stretched across infinite darkness. And yet, perhaps this final emptiness is not an ending, but a reset, a quiet moment before the next creation. If quantum fluctuations can give birth to universes, as they once did ours, then the death of one cosmos may seed another. In this cyclical vision, black holes play a central role, both destroyers and creators, collapsing old realities and giving rise to new ones. In their silence lies the heartbeat of eternity. Bridging the infinite black holes also challenge our very perception of reality. They hint that the universe may not be continuous, but digital at its deepest level, composed of discrete packets of space, time, and information. If so, then everything, from galaxies to thought itself, is the outcome of information evolving according to mathematical laws. At the event horizon, this interplay becomes visible. Each fluctuation, each quantum bit, contributes to a grand computation that has been running since the dawn of time. And if the universe is indeed such a computation, then black holes are not anomalies. They are core processes maintaining the balance of logic that defines existence. To understand them is to understand the algorithm of creation itself. The philosophical horizon beyond the equations and data, there lies a deeper question, one that transcends science and touches philosophy. If information can never be destroyed, then nothing in the universe is ever truly lost. Everything that has ever existed, every star, every planet, every thought, still exists somewhere, encoded in the great web of space-time. Black holes, then, are not graves, but archives, cosmic libraries where reality stores its memories. They remind us that even in darkness, information endures, order persists, and knowledge remains imprinted on the universe's fabric, perhaps consciousness itself, our capacity to think. To question, to understand, is another form of this universal information flow. In seeking to decode black holes, we are, in a way, decoding ourselves, the part of the cosmos that has become aware of its own workings, the return of light, and so the image of a black hole, that dark center surrounded by a glowing halo of light, takes on new meaning. It is not a symbol of destruction, but of transformation. The light that bends around the horizon, the photons trapped at the edge of eternity, are not dying. They are being reshaped, reborn, redistributed into new forms. The same principle applies to all of existence. Energy becomes matter. Matter becomes information. Information becomes energy again. Nothing is ever truly lost, and it only changes its state, its encoding, its rhythm. In this eternal cycle, black holes are both guardians and gatekeepers of the universe's data, the ultimate processors in a cosmos built on logic, symmetry, and endless renewal. Humanity and the infinite, from our small planet, we have dared to imagine the unimaginable, to predict and even see the shadow of an object that consumes light itself. Our telescopes, equations, and collective imagination have reached into the most extreme corners of reality. Each discovery we make brings us closer to understanding the grand design, and yet every answer opens 1,000 new questions. What happens beyond the horizon? Can the laws of physics truly be complete? Is information the foundation of existence, or merely the way we perceive it? These are not just scientific inquiries. They are reflections of our own nature, our hunger for truth, our defiance of limits, and our unending curiosity about what lies beyond the visible. In the end, black holes are more than astronomical objects. They are metaphors for knowledge itself, vast, mysterious, pulling everything toward their center, yet surrounded by light that refuses to vanish. They show us that even in the deepest darkness, there is structure. Even in the silence of annihilation, there is meaning, and perhaps that is the ultimate message of the cosmos. That the universe is not a place of endings, but of continuous transformation. That death is never final, and information, the pure essence of reality, can never truly be destroyed. As we gaze into the abyss of a black hole, we are not staring into nothingness. We are witnessing the universe at work, processing, preserving, and rewriting the story of itself, one bit of data at a time.